and
Are you screen sharing? Yeah, can anyone else see it?
Let me just share my screen as well.
Fancy mug.
Go live.
It is a very fancy mug.
Should be able to see my screen now, right?
Still loading for me, but
all right. Just say when it's loaded, and then I guess I'll start.
can anyone else see it? I see like the icon on the side has the screen, but when I click on it, it's not there, which is probably...
I can see it.
I can see it.
Right.
All right. Okay. So I'm going to be talking about spectral sequences, as the title of the talk suggests. And so spectral sequences are a much more computational side to homotopy theory and algebraic topology and whatever. But nowadays they're used all over the place. There's spectral sequences in algebra, geometry, even physics, I guess. Whatever. But in today's in this talk, I'm going to be going over two examples of spectral sequences, which both emerge mainly in topology. So the first one is So firstly, I'll give some basic definitions of motivation. That shouldn't take too long. And then we'll move on to the Serre spectral sequence, which will be our first example of a spectral sequence, and it's a really useful one. There's tons of applications. So the idea is, if we have a vibration, oh god, this Adobe Reader pen is not the best thing, but whatever. If we have a Serre vibration which looks like this, and we know the cohomology of two of these things in the vibration, then hopefully we can bootstrap our way up to the cohomology of the other one. And then after we look at some of the applications and whatever of those of that spectral sequence, we'll move on to the entire Hurewicz spectral sequence. I think that's actually a typo there. It should be a ZE, not an EZ, but whatever. So that's basically the plan. So, firstly, we'll talk about some motivation. And so motivation here is to start off with a cell complex, CW cell complex X. So for obvious reasons, we want to compute its cohomology ring, because that's going to tell us a bunch of information about that space X. And that's what we want to obtain. So it's graded via the cat product, which means that so if we write if we write this for the direct sum over all of the cohomology groups of X, then the cat product is a product which takes in an element of the nth cohomology. This pen is, it's just like the Adobe Reader default one, but hopefully it suffices for the talk, but whatever. And it takes in an element of the nth cohomology and the... Oh god, okay. That's really bad. I don't know, so the Adobe Reader pen seems to be terrible.
Right, just to interrupt, are you talking about the cap product or the cup product here?
Sorry, cup, sorry, yeah, that's also typo, yeah, cup, yeah. I'm just going to quickly switch to Epic Pen, because the Adobe Reader pen is awful.
Now you see why I always use Epic Pen, even though it has the disadvantage of not saving annotations. It's much nicer.
Yeah. I guess people just have to watch the video for the annotations, but okay. So it takes, so this should say the cut product, by the way. Anyway, so the cut product, what this graded word means is that it takes in an element of the nth cohomology and an element of the mth cohomology, and this product should land in the n plus mth cohomology. So computing. So obviously, we want to compute this cohomology ring, but it's difficult in general. So the method for making this task easier, basically, is spectral sequences. And this is the task that this is the method which we're going to use in this talk. So if we have a CW pair, AX, then we can get a long exact sequence in cohomology which looks like this. And so the idea is, if we know the cohomology groups of A, which should be a simpler space than X, then hopefully we can obtain some terms in this long exact sequence, and then hopefully we can bootstrap our way up to the cohomology of X. But even if A is simpler than X, it still might not be easy. So we can introduce another CW pair here, and then a CW pair here. So hopefully this A0, we hope that this A0 is simple enough to bootstrap our way up to the cohomology of A1. Then hopefully with this cohomology of A1, we can try and bootstrap our way up to the cohomology of X. So with this double filtration here, you could say, we have two long exact sequences. But we don't need to stop with two. We don't need to stop with two spaces, right? We can do this for n spaces. And so we would hope that we can approximate the cohomology of X with a bunch of these CW pairs like this. And hopefully with all of those long exact sequences, we can eventually, bootstrap our way up to the cohomology of X. So that's going to be our general approach. And so the algebraic tool, so the way that we put all of these long exact sequences together, the name for this tool and the way that we put it all together rigorously and all of that stuff is via the spectral sequence. So that's our general goal, and kind of a little bit of motivation for the definition, which is going to come up on the next slide. So a spectral sequence is a collection it's normally triply graded, so we're always going to have the rth page, and normally, actually no, it's not triple, it's bi-graded. By these P and Q, but it doesn't always need to be bi-graded. For example, there's an example called the box sign spectral sequence, which is it isn't even singly graded, it's just ER plus 1 and so forth. But that's kind of a special example. 99% of the time your spectral sequence is going to be bi-graded. So obviously it's going to have to satisfy some rules. Firstly, for all of these R, P, and Q in integers, this the P.
Craig, sorry, can I interrupt for 1 sec? The people are mentioning in the chat that we can't see the writing. Are you drawing with Epic Pen now, or are you just pointing?
Okay.
Make sure when you screen share, you share the whole screen and not just the window, because otherwise the drawing will show up.
Yeah, good note. Okay, 1 sec. Screens, yeah, my bad. Okay, you should be, let me just write something. You can see that now?
Yeah, that looks better. Good.
Okay, yeah, sorry about that. There weren't too many important annotations in that time, so, should be all good. But anyway, so for all of these integers R, P, and Q, R is normally a natural number, but for P and Q in the integers, we have an abelian group ER, PQ. Now the differentials are a bit more complicated. They're going to go, so this is actually, technically we should call this a cohomologically graded spectral sequence, because the differentials are of by degree R minus R plus 1. So that is, they take in this EPQR, and then they're going to add r to the p-axis, basically here, and then they're going to subtract r and add 1 to the q-axis, like this. And the third condition, and this is an important condition, is that the homology, and because dr squared is equal to 0, we get a chain complex formed by these drs. And so we can talk about the homology of ER with respect to these drs, and this should be precisely the next page. Okay. So, let's take a look at what this looks like. So always the q-axis will be along here. Let me make the pen slightly smaller for this. The q-axis will be along here. And let me just redraw this. Alright, so this will be the q-axis. This will be the p-axis. If we have 0, 1, 2, this is just a tiny sketch. So the E1 page, what will this look like? So we're going to have all of these dots are these abelian groups, and the differentials, they're just going to go across by 1. Because, and so on and so on. And this is because, well, D1, what it's going to do is it's going to take in PQ, and it's going to output P plus 1 Q. So it's going to do Q minus 1 plus 1, but that's obviously not going to do anything, so we just go across. And so that hopefully shows why normally when we're talking about spectral sequences, we immediately talk about the E2 page, because this E1 page is most of the time just a well understood complex. Okay, so now let's sketch the E2 page. Alright, so again along the q-axis we're going to go here. So now we'll introduce 3, 2, 1, 0. And then along here we'll have 0, 1, 2, 3. So again we're going to have abelian groups being all of these dots. And so, okay, this time it's going to go across 2 and down by 1. So this differential here is going to go there. This 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 is going to go there. Because we're going across by 2. And then we're going to go down by 1. Because the D2 is going to go from EPQ2 to EP plus 2. So that corresponds to going across by 2. And then it's going to be Q minus 1, which corresponds to going down by 1. Because, well, again, minus 2 plus 1 is just minus 1. The E3 page, okay, I'm just going to be lazy and draw on with yellow differentials. So the E3 page is going to go across by 3 and then down by 2. So this one is going to go here. This one is going to go somewhere over here, and so forth. And, okay, so this will lead me nicely onto the what's it called? Notion of convergence. So if there's like an area here where all of these abelian groups here are 0, then you'll see that these differentials will suddenly either start going too far down or they'll start going too far across. And when all of the differentials are going too far down or too far across, then we say that the spectral sequence collapses at the rth page. So in the next slide, we'll see a rigorous definition of this. So normally there'll be an r much bigger than 0 or bigger enough than 0, such that all of the differentials dr prime will be trivial for r prime bigger than or equal to r. And yeah, that on the picture I just showed before, that's what it will look like. And when this happens, then, okay, the ER, let's see what will happen. So the homology of ER is going to be itself, right? Because if we have a chain complex, which looks like this, and both of these differentials are trivial, then, well, the kernel mod the image, well, the image is going to be 0, the kernel is going to be the group itself, so we're just going to get the group itself, and so the homology at that position will be ER, but then when all of these differentials are trivial, then obviously we're just going to get back our ER, our original complex. And so, but by definition, this must be the r+1th page. And so, because all of these dr primes are trivial, then we're just going to get this repeated. We're just going to keep going and keep going. And so, because of this page is called the E-infinity page. And now this leads us on to a very important notion of convergence. And in this talk, I'm going to simplify it a little bit. I won't get into all of the nitty-gritty errors that could arise, known as extension problems. Because in this talk, we'll just deal with examples where extension problems don't come up. So a spectral sequence converges to a graded object, H star, if we can recover each Hn by summing along the diagonals of the E-infinity page. So let's just say that, so if we have the E-infinity page looking like this, something like this, if we wanted to recover the H2, then we would just sum along all of these people here, because this would be 2, 0, this would be 1, 1, and this would be 0, 2. So this is the precise definition. Hn is equal to the direct sum over all p plus q equal to n of the E-infinity page, which is basically just summing along the diagonals. And cautionary word is that extension problems do arise. But in this talk, we won't run into them because that's a whole different issue, which I couldn't be bothered to deal with in this talk. So in this case, if there is such a graded object, then we write this. And this is just shorthand for saying this, basically. And notice again that we're talking about the E2 page straight away, because again, the E1 page is normally already well understood. So now we've got the basic definitions out of the way, we can talk about a really important example of a spectral sequence. There's plenty of applications. You'll see what all of this work is about immediately. It's just a very important example. And it's called the Serre... Oh, okay, my bad. What I was talking about was the Serre spectral sequence. But I might as well go over the general strategy. In general, for spectral sequences, because this is it's normally this graded object that we're going to care about. So, in turn, what we're going to care about is the E-infinity page. And so, in turn, what we're going to care about are the differentials, because we want to know when exactly the differentials will be trivial, and what they're going to look like before they're trivial, so that we know all of these pages, say, for example, the ER-1, we want to know that. But we need to know the differentials in order to obtain that. So there's all sorts of pieces to the puzzle, which we need to figure out before we can do this summing along the diagonals, which we would like to do. So, by compute every page, not only do I mean each E1, E2, PQ, but I also mean the differentials D1, D2, and so on, until these things become trivial. Then we can recover the homology or cohomology by summing along these diagonals. Again, difficulties can arise by just doing this naive approach, but in this talk it will be fine. I don't want to make it sound like it's too easy, right? We're just going to run into some difficulties. For example, how the hell are we supposed to compute the differentials? These two are related, very related. When exactly will the spectral sequence collapse? And one that I forgot to add, but it's really important, is And we don't cover in this. I'm not going to cover in this talk, because I'm more focused on talking about why these are useful, not about how we build them up. But how are we actually meant to construct it? Right? How are we supposed to construct a spectral sequence? It's all good having this theory built up, like having this definition here, but if we have no examples of spectral sequences, then it's going to be pretty useless, right? Thankfully, okay, there's plenty of ways to construct spectral sequences, which we won't talk about any of them. We'll more just assume that they've already been constructed for us, and then we'll talk about the applications of that. So, okay, now that I've rambled a little bit about the basic definitions and the prerequisites for the main bulk of this talk, we can proceed by talking about the Serre spectral sequence. So, okay, yeah, as I said before, it's to do with using a Serre vibration, and then hopefully if we know the cohomology of two of these things, then we can get the cohomology of the other one. So more precisely, the E2 page is given by the p cohomology with coefficients in the p cohomology of B, the base space, with coefficients in the q cohomology of the fiber, and it converges to the cohomology of the base space. Sorry, not the base space, the total space. Okay, so let's do an example computation, because really the best way to learn about how to implement the strategy that we outlined above, how to implement all of these definitions, is for you to just do the spectral sequence, to just compute it. That's really important with spectral sequences, and so I'm just going to get straight into doing these computations. So, the first example is computing the cohomology ring of CP infinity. And so I claim that the cohomology ring of CP infinity is equal to this polynomial ring here, but this x, it lives in the second cohomology of CP infinity. Okay, so we'll see how to get this from spectral sequence. So firstly, okay, so before we do any of this strategy we need to, because it's a Serre spectral sequence, it's of a Serre vibration, we actually need to know which Serre vibration we're working with. Thankfully, we have a convenient one at our disposal, which is, in general, it's the S1 to S2n plus 1 to CPn. But when we let n equal infinity, we just get this. Now, the cohomology of S1 is simple, the circle is simple, and also, the infinity sphere is homotopy equivalent to a point. So these are really simple stuff, the cohomology of those guys. So we've got the cohomology of him, we've got the cohomology of her, so now we just need the cohomology of this guy. And we're going to implement our strategy from before. So remember that we wanted to compute all of the pages until it collapses. So let's look at the E2 page, right? By definition, or, well, not really by definition, but by the theorem above, it's going to be the p cohomology of CP infinity, and it's going to have coefficients in the q cohomology of the ones here. But, this is going to be the integers for q equal to 0 or 1, and it's going to be trivial otherwise. Right? So therefore, when q is bigger than or equal to 2, EPQ is also going to be 0, right? Because it's just going to be with coefficients in this trivial group here. And so, the E2 page is given by the p cohomology of CP infinity again, this is with integral coefficients, and this is when q is equal to 0 or 1, and it's going to be trivial otherwise, because of what I just said before. Now, we know what this spectral sequence converges to as well. So we know that we want everything to die on the E infinity page, except for, okay, we can exclude E0, 0, infinity, but everything else needs to die. Be that, if that needs to be by making a differential surjective or injective or whatever, so be it. We just need everything except maybe E0, 0, infinity to die. So firstly, we need to figure out when this spectral sequence collapses. And then we need to figure out how to make this true. Okay, so what's the E2 page going to look like? Well, let's say we have the q-axis here. Well, the only ones we care about is when it's 1 or 0. Actually, I've got space here because we only have 2 things here. So when it's 1 or 0, and then we're going to have 0, 1, 2, 3, so everything up here is going to be 0 because that's when q is bigger than or equals to 2. Okay, so along here we're going to have the 0th cohomology of CP infinity. Here we're going to have the first cohomology of CP infinity. Here we're going to have the second cohomology, CP infinity, so on. Again, here we're going to have the same thing, we're just going to denote it by H1, H2. Sure. And so what are the differentials going to look like? Well, the differentials, they're going to go across 2 and down 1. So they're going to go here, here, here. Of course, remember that when we might as well see what happens when we have E3. So if we have the D3 differentials in pink, then if we try to make any of the D3 differentials non-trivial, well, then what's going to happen is we're going to go across by 3, no problem, but we're going to go down by 2. So we're going to go down too far, and this is going to be trivial now. And again, we can't come from here because this is equal to 0, and so the D3 will be equal to 0. So, therefore, when R is bigger than or equal to 3, each of these D3s is equal to 0. It's trivial because our differentials are going to go too far. Okay, so that's good. So now we know that it collapses at the E3 page. What else can we find out? Yeah, so this is what we said here. So any element of the E2 page. Okay, no, this is just a confusing statement. You'll see what I mean by this though in a second. So what we want to compute is E2 0 and E1 0, and hopefully we can get some generators for these groups, and then hopefully we can use the generators to get the higher people on this page. So just as a recap, this is equal to the second cohomology of CP infinity, and this is equal to the first cohomology of CP infinity. So this is what we're going to start off with. Okay, so firstly we're going to do this one. So the differential D2, which takes in E201 and it outputs E220, is an isomorphism. But okay, what good is this? Well, this is just the 0th cohomology of CP infinity. And okay, it's pretty simple to get that this is the integers. So basically what I'm claiming is that this too is isomorphic to the integers. So let's do that. And we're going to see how knowing the cohomology of S infinity is also going to help us. So, for D2 to be an isomorphism, what we require is that the kernel of D2 is equal to 0 for injectivity, and the co-kernel of D2 is also equal to 0 for surjectivity. So let's do it for injectivity here. So remember that E301 is equal to 0 because this is equal to, from what we figured out before, this is equal to E01 infinity. But then, remember from before, because this spectral sequence converges to the cohomology of S infinity, we need that everything on the infinity page gets killed. Everything on the E infinity page gets killed, so this must be 0. But also, remember by definition that this is also equal to the cohomology of E201. So at this place, basically. And so what's this going to look like? Well, it's going to be the kernel of the map that we want, mod the image of this map, but because the Serre spectral sequence is what's called a first quadrant spectral sequence, which means that we can't have negative integers in the subscripts without it being trivial, this thing here is going to be 0. And so this image here overall is going to be 0, because we're mapping from a trivial, the image is equal to 0, because we're mapping from a trivial group. And so we've got the kernel mod 0 is equal to something 0. So obviously that makes the kernel equal to 0. So that's good, we proved injectivity. And then we're going to use the exact same reasoning to show surjectivity, aka that the co-kernel is equal to 0. So again, remember that E203 must be 0, right, because of the same reasoning as before. And again, because of the same reasoning before, it's equal to the kernel of this modulo the image of what we want. Now, because this group here is equal to 0, the kernel of this is precisely E202, right? Because
sorry, I'm late.
Yeah, so everything here, so this D2 is going to map everything to 0, right? Because this is 0. And so on top of this quotient, we're going to get back our E202. And then on the bottom, we're still going to have the image of our map. But then this is precisely equal to the co-kernel of D2. This is just the definition of the co-kernel. And, but from before, because it's equal to this also must be 0. And so it's surjective too. And so we've shown that D2 must be an isomorphism, which is really good. This is what we wanted. So, okay, just to recap, what does this mean? This means that the second cohomology of CP infinity is equal to the integers. Well, okay, technically means it's isomorphic to the E012, but that's obviously going to be the integers. We don't need to compute that one because we can use our common sense for that one. Okay, so let's move on. So that's good. We've shown something using spectral sequence argument, but obviously we're not done with our overall thing which we wanted to show. So we'll proceed. Now we want to show that this person here is trivial. So that is that the first cohomology group of CP infinity is equal to 0. And to do this, well, okay, remember that if it did turn out that the homology of the E2 page at this point 10 with respect to D2 is equal to itself, then because this is equal to by definition this is equal to E310, this is equal to 0. So this is what we want to show. We want to show that the differential, okay, so if we look at it as a chain complex down here, the differential D2 going to 1, 0, 2. We want to show that this differential here is 0, and we want to show that the differential going out of it is also equal to 0. Because that would make the homology of this guy at this point equal to itself. So, let's just look at this this differential going to this guy. Well, that is the differential which goes from E negative 1, 1, but because it's only a first quadrant spectral sequence, this person here is equal to 0. So the overall differential is going to be equal to 0 too. Furthermore, the differential going from E102, so the person with the differential going from here to some group there, well, what's this going to be? Well, it's going to add 2 here, no problems there, 3 is positive, but it's going to subtract 1 here, and that's not good. That's going to be not good, and that's going to be 0, so overall, this differential is also trivial. And so, looking at it as a chain complex like this, we get that E10 is equal to E103, but then we showed that earlier that this was equal to E10 infinity, and that's precisely 0. So, we managed to show that to recap what this showed, is that the first cohomology group of CP infinity is trivial. Alright, that's good. And now, we're actually closer than you might think to being done. Let me just take a sip of water. Okay. So actually we can use both of the arguments which we just used can be used inductively to show that E2n0 2 is equal to is isomorphic to the integers. And remember, don't forget what we're actually computing, which is that E2n0 2 is equal to the second 2nth cohomology of CP infinity. Right? That's what we're actually computing here. And again, by induction and using the same argument as before, we can show that all of the odd cohomology groups of CP infinity are equal to 0. So that's excellent. We're really close now because we've computed all the cohomology groups. Now we're just going to try and deduce the ring structure of the cohomology ring. Sorry, the ring structure of the cohomology ring by looking at some generators. If we let Y generate our E01, 2, then D2, this isomorphism, will send this generator to a generator of E20, 2. And so, okay, let's look at what this actually means. So, if we draw a mini little axis here, so we have 0 here, 1 here, 0 here, 1 here, 2 here. Alright, so, let's see. So, going along X will take us to E20. And then going up Y will take us to our H2 here. So going across X and up Y will take us to this page here. And this again is the second cohomology group of CP infinity. Okay, good. So we've been taken there and we get this generates this. Now here comes the punch. When we apply the differential, we're going to get a generator for this. Okay, that's expected. But the differential satisfies the Leibniz rule, which is that d of xy is equal to dr of xy is equal to dr of xy plus or minus. There's going to be a sign issue here, but I think it's up to degrees. I think it's plus -1 to the degree of x times the degree of y. Up to the side, it's going to be plus or minus, and then we're going to have dr of y times x. So let's see what this looks like here. Well, okay, d2 of x is going to be, let's break this up further, that's going to be d2 of y. Because x is precisely d2 of y. But then remember that d2 squared is equal to 0. So then this whole thing is going to die. But then remember that d2 of y is equal to x. So this thing right here is going to be x cut x. And this is going to be x squared. So actually, what we're getting is that x squared is going to generate the fourth cohomology of CP infinity. Because remember, that's what we're computing here. This is equal to the fourth cohomology of CP infinity.
Wait, Greg, I had a question. I had to go on deference. I think I may have missed something, but why on the bottom is the absolute value of x equal to 2?
Oh, this is the at the start, it's basically, the cohomology ring is graded. So this thing here, the cohomology ring of, let's just say x for now, is equal to the direct sum of all of these cohomology groups here. And so, what this means is actually that the degree of x is equal to 2, which means that x is going to land in the second cohomology group of CP infinity. So that's where it's going to land in this, yeah. So that's what it means. It's the degree of x equal to 2. So anyhow, so we get that x squared generates the fourth cohomology of CP infinity. So I think that you could see, if you continue this by induction, you get that x to the n will generate the 2nth cohomology group of CP infinity. And so overall, from this we can deduce the ring structure to be precisely what we wanted. Whew, that was quite the computation. But okay, on the next slide I have a recap of what we just did. Okay, let me just take another sip of water first. What we did was,
since you're recapping, can I ask a strategic question just to situate things? And your answer to this might be, I'll do an example that explains this later, but I'm just trying to keep the big picture in mind. So far it seems like this is a gadget, that if you have a fibration, you can relate cohomologies of the fiber base and total space. And I think you've just convinced me pretty compellingly that the E2 page tells you about the cohomology of the base space, if you could figure out the other stuff. And I think you said something about if this thing converges, the convergence is going to tell you something about the cohomology of the total space. But I just wanted to ask, since it seemed like the dependence on the fiber was more subtle, because wasn't it that the fiber really only entered through the coefficients, I guess, for the cohomology groups in the E2 page? Is there ever a case where it is useful to get cohomology for the fiber out of this structure, or is it usually that you get out data about the base or the total space?
I'm just trying to think of an example. Here's a good. There's a nice example. When you have, so for example, if you have the loop space, path space fibration, like this, actually, what we can do here is, because we know the cohomology of these two people, what we can do is, I don't actually have an example of this in the talk, but if you say have x equal to the n sphere here, these two, the path space of the n sphere, well, that's contractible, so that's easy, and the n sphere itself, the cohomology is easy too. We can this is quite simple, because the cohomology of the pth cohomology of the n sphere with coefficients in the qth cohomology of the loop space of the n sphere. What's that going to be? Well, that's going to be the qth cohomology of the loop space of the n sphere for p equal to 0 or q, and it's going to be 0 otherwise. And so now we're getting data about this thing if you continue with the spectral sequence argument.
Oh, good. I see. Okay, so the right way to think about this is that there are situations where if the cohomologies of any two of the guys in this fibration are sufficiently simple, you can reverse engineer and get the other one.
Yeah,
That's probably the way to think of it.
Yeah.
Okay, thank you.
That's how I like to think about it. I mean, it's highly likely that there's some like really weird, example where that strategy doesn't work. But from the examples that I've seen so far, yeah, that's basically the strategy there. Anyway, so yeah, so overall, what we did in this example was we looked at the E2 page first. We saw which elements of the E2 page we actually cared about. And so, thus, we could look at which differentials we also cared about. Like, we managed to conclude that D3 would be breaching too far. So we managed to show that the spectral sequence in this case was quite simple because it collapses really early. So that was nice. And then we managed to bring in the cohomology of the total space. To get some information about the E2 page, because we knew what had to happen at the E3 page, and so from that we could work backwards kind of to get information about the differentials of the E2 page, and so on, and therefore information about the E2 page itself. And so with all of this information, we managed to piece together all of the final results, and we managed to use generators and stuff like that to deduce the ring structure. And actually, the next thing we're going to look at, another application of the Serre spectral sequence. I remember, I don't know why I was so surprised that this could be proven using the Serre spectral sequence. But the next application we're going to look at is the Hurewicz theorem. And we can actually show this theorem here, that if x is n-1 connected for n bigger than or equal to 2, then the nth homotopy groups of x and the nth homology groups of x will coincide. And also the ith reduced cohomology group of x is 0 for I less than or equal to n-1. Okay, so in this example you're seeing homology, but thankfully there's a homological version of the Serre spectral sequence, and it's going to be the DRs that are going to be of by degree negative r minus 1. So they're going to go to the left and they're going to go up this time, basically. Sorry, that should be negative r plus 1 r. Yeah, should be like that. So it's just going to be homologically graded because we're dealing with homology this time. But hopefully that shouldn't trip you up too much. So okay, which fibration are we actually going to use? Well, we're going to use the one which I talked about before, just earlier, which is this fibration here, it's useful because the path space is contractible, so we immediately get this middleman here. So if x is sufficiently nice, then we have two people and we can deduce stuff about the loop space of x. But also by induction, it turns out that the loop space will be the nice guy here. And so we can deduce stuff about the cohomology of x. Also remember that the loop space behaves nicely with the homotopy groups, and so hopefully we can use that to our advantage too. Okay, so the base case is when n equals 2. So recall that the second homotopy group of x is isomorphic to the fundamental group of the loop space. And because this is guaranteed to be abelian, the abelianization is, because it's equal to a second homotopy group, this one is going to be abelian. And so we know that the first homology is the abelianization of the fundamental group. Well, of course, the abelianization of an abelian group is just that group itself. And so we get this isomorphism too. And so to show the base case, all that we need is that the second cohomology of x is isomorphic to the cohomology of the loop space of x. So now so here comes the spectral sequence. The E2 page is given by this here. So, okay, what are we going to get? So, along here, we're just going to look at, we're just going to go up to 2, 1, go down a little bit. Actually, not, yeah. Alright, we'll say 2, so we'll go 3, 2, 1, 0, like this, and then we'll go 0, 1, 2, 3, like that. And then, okay, so, what are we going to get? So we're just going to go on the rows here. So along when Q is 0, we're just going to get the 0th cohomology of X. The first cohomology. Sorry, I don't know why I'm writing cohomology. This should be homology. Sorry. First homology of X. Second homology of X, third homology of X, and so forth. And then up here, when P equals 0, we're going to get the first homology of the loop space of X, the second homology of the loop space of X, and so on. What we want to show is that the differential, which because we're homologically graded, it's going to go left and up instead of right and down. We want to show that this is an isomorphism. But okay, I'm not going to do this argument again. The path space is contractible, so we can literally just repeat the same argument that we did before, when we were showing that the second and the 0th cohomology of CP infinity coincide. We can use the exact same reasoning as before to show that this D2 must be an isomorphism. And so, okay, we have that. So what do we show? Well, because remember that this right here is isomorphic to the fundamental group of the loop space of X, which is isomorphic to the second homotopy group of X. And so we get this isomorphism too, which shows the base case, which is good. So, okay, nice. Now we just need to do the inductive step. So, we're going to do it for n-1, and by this, I mean that X is n-2 connected. Because the original statement of the theorem was that X is n-1 connected, so by this I mean we're assuming that it holds for X being n-2 connected, for n bigger than or equal to 3. We're showing that it's true for any n. Okay, so again, remember that loop spaces behave particularly nicely under homotopy groups. So if X is n-1 connected, then the loop space must be n-2 connected. But because of the induction hypothesis, we know that the n-1th homotopy group of the loop space must coincide with this. But again, this works out wonderfully because the loop space will just loop space behaves so nicely that we just get this result straight away by the induction hypothesis. And so now we just have to do the same thing as before. That is, we have to show that the nth homology of X is isomorphic to the n-1th homology of the loop space of X. Okay, so let's see what we're doing here. Well, the spectral sequence is going to come back now. So by the induction hypothesis again, when Q is less than n-1, this, oh god, that's bigger than I anticipated. This right here is going to be trivial by our induction hypothesis, and so everything is going to die. And so on the p-axis, So along here, along this axis, so all of the people here, so the zeroth cohomology up until the nth homology up until the nth homology is not going to get affected by the differentials, because they're just going to be because they're going to be mapping to something trivial, so they're not going to get affected. But the spectral sequence has to, but everybody on the p-axis does have to get killed somehow. And because it's converging to this path space of X, which is contractible. And the only way for this to happen is for the dn here to be an isomorphism, and the homology of X to be 0. We have to just kill that off. If the differentials don't do it, then we'll just have to assume that it's that's just how it was. And this is because the last page, everything must die except for E00. And so again, so what we did was we used that on the E infinity page, E infinity PQ must be trivial, where PQ is not equal to 0. And so the only way for this to happen is for this dn between the hn of X and the n-1th homology of the loop space of X to be an isomorphism by the arguments that we've already done before, and for all of these people that are never going to get touched by the differentials to be 0, to just be 0, and so that's how we show that. Okay, so for those of you, so this is going to be the final computation that I do for the Serre spectral sequence, and for those of you that have, that are on my server, all of you are on my server, but for those of you watching on YouTube who are not on my server, or not very active on the server at least, you might not know how obsessed I am with homotopy groups of spheres. So, of course, when I first saw this computation, this is probably one of the first things that even got me into learning about spectral sequences. Just so I could learn a little bit, because as you start going up in dimensions, these homotopy groups of spheres, they start relying more and more on spectral sequences, and Steenrod squares and that type of thing, whatever. All of this advanced machinery. And one of the first examples of a spectral sequence that I learned was how to show that the fourth homotopy group of the 3 sphere is isomorphic to the integers mod 2. So immediately you might be thinking, well, spectral sequences tell us stuff about the cohomology, so surely it's unreasonable to assume that we're going to get results about homotopy. But, that's not really correct. All we need is just a little bit more setup. And thankfully, the Hurewicz theorem has done that nicely already for us. So this is just the setup. This is just setting everything up so that we have a convenient, fibration. We have convenient everything to do our work. And so the theorem that we're using is, if X is simply connected, and it has trivial homology for all k between 0 and n, then we have a map which induces an isomorphism on homotopy groups, which looks like this, where F is the homotopy fiber, so that factors like this, and F is the homotopy fiber, so its homotopy groups are going to be 0, it's going to be trivial when k is less than or equal to this n here. But then as soon as we get k bigger than n, so as soon as these homology groups start to actually not vanish, then the homotopy groups of this homotopy fiber are going to be precisely the homotopy groups of X. And by the Hurewicz theorem, well, okay, F is N connected, and so, sorry, this should be an N, not a K. It's N connected, so its homology group, N plus 1th homology group, is going to coincide with its N plus 1th homotopy group. But then, because N plus 1 is bigger than N, this is going to coincide with the N plus 1th homotopy group of X. So, that's good. That's really good. This is a really convenient way to set up everything which we're going to do for now. So okay, we're going to let's actually see what we're doing. Okay, let's just see how this fits into our computation. What it does is, so we have a fibration here, and the reason for this is, okay, let's look up at where this 3 is coming from, where this integer is coming from. Well, remember that the cohomology groups of the 3 sphere are equal to 0 for for k between 0 and 3. Right, because when n equals 3, then this is going to be the integers. Anyhow, it induces an isomorphism. So anyway, we get this fibration here, and the n here is going to be 3. Our x is going to be S3. We know that the third homotopy group of the 3 sphere is isomorphic to the integers, and that 3 is equal to 3. So that's where so we're going to get k of z3, right? So that's where that's coming from. It's all from this theorem. This is just the setup. The actual juicy spectral sequence stuff is going to come in a second. And we get the homotopy fiber there, F. Now, up to homotopy, just something we can do is, if we take the loop space of this guy, like so. Well, this is going to be homotopy equivalent. First of all, this is going to be homotopy equivalent to k of z2, and this is precisely CP infinity. I think I actually did show this in a much earlier talk on fiber bundles. If you were there, I showed that k of z2 is CP infinity, but whatever. And then it's going to go to the homotopy fiber F, and then it's going to go to S3. But now, we have a fibration where we know the cohomology groups of this guy, and we know the cohomology groups of this guy. So this is what our strategy is. We're using this strategy again. So, we're going to try and get the 5th cohomology group of F. And by some arguments, universal coefficient type arguments, we can drop torsion a degree, and we're going to get the 4th homology group of F, and this is going to be precisely our desired thing. So we're going to try and get this guy, and then hence get this guy. And then hence get this guy here. That's our goal. So here comes the computation. Firstly, we're going to do what we were doing before, get the E2 page. And this is precisely, here you go. Here's an example where, here's the fiber, but it's appearing here, like that. So, yeah, I guess there you go. Anyway, it's gonna look like this, right? Because the pth cohomology of S3 is equal to the integer, with coefficients in some ring R, it's going to be R when P is equal to 0 or 3, and it's going to be 0 otherwise. Okay, so that's where we're getting that from. But remember that we computed the cohomology of CP infinity from before. And it's gonna be the integers if Q is even and 0 otherwise, if Q is odd. So, the only non-trivial terms of the E2 page are when p is equal to 0 and then q is equal to 2n, or when p is equal to 3 and q is equal to 2n. So those are our non-trivial boys. And okay, this is what the E2 page looks like. Well, okay, so let's have q going from 4, 3, 2, 1, 0, 0, 1, 2, 3, 4. So obviously all of this stuff here, well, this is when p is not 3 and not 4. Sorry, this one p is not equal to 3, and all of these integers are not going to be equal to 3 or 0. So this area here is all we're going to care about. So what exactly is it going to look like? Well, along here we're going to get the integers. Here we're going to get the integers. Here we're going to get the integers, and so on upwards. And these intermediate ones are going to be 0. And then along this 3 here, when p is equal to 3, we're going to get the integers, 0 again, the integers, 0 again, and so on and so on. So, what are our non-trivial differentials? Well, let's try d2. This is going to go across 2, 1, 2, and down 1. That's not good enough. That's not long enough. What's going on? Our d2 is not stretching far enough. Let's do green. I like green. Okay, now let's try d3. This is going to go across 1, 2, 3. Excellent. It's going across 3. That's exactly what we wanted. Now is it going to go down enough? It's going to go down by 2, so it's going to hit our integers again. Booyah! That's the one that we wanted. We want d3. These are the non-trivial boys. d3. So dr for r bigger than or equal to 4. Okay, so when r, okay, let's try I don't know, purple, let's say. When r is equal to 4, well, then we're going to go across 1, 2, 3, 4, but then we're reaching into this zone here where it's way too far. And then when 5, we're going to go even further into the zone, so, you know, it's going too far at that point. So when r is bigger than or equal to 4, our terms are, everything is going to, vanish. So the E4 page is equal to the E infinity page. Okay, so now that we have that information at hand, what we want to do is, we want to see what the differentials, so we want to know what D3 is, basically. So let's take a look. Okay, yes, that's basically summarizing that. Okay. What we're going to do is compute the differential. Okay, so I like this quote here. Compute the differentials without computing the differentials. So what do I actually mean by that? Well, I mean, we're gonna compute the differentials, but we're only going to do them on the generators. And hopefully that's going to be enough information for us. So okay, let's let U generate E330. And then, okay, so U to the N is going to be 0. Because at that point, say for example U squared, that's going to land in E603, and that's in the zone where it's too far away. Now if x, okay, so U to the N is 0 for N bigger than 1. Now if x generates E023, then x to the N is going to generate E302N. Why? Well, because x squared is going to land in E043. X to the 3 is going to land in E063. And remember, these E023 2n is equal to the 2nth cohomology of CP infinity. And remember, we deduced the ring structure before, so x to the n is going to generate that guy. So ux to the n generates E3 2n. So what? Okay, let me just sketch this out quickly. So if we have, let's just say let's say we have 4, 3, 2, 1, 0, 0, 1, 2, 3, 4. Now, okay, so u is going to send us along by 3. Then doing x to the x once is going to send us up by 2. Doing x twice is going to do x squared, like this. So this is ux squared, this is ux cubed, and so forth and so forth. So that's what it's going to look like. Doing u is going across, doing x is going up. And so what we claim is, and I'm not going to show it, but I don't think it's that difficult to show, is that d3 of x is going to be u, but it's going to generate E303. I'm not actually sure which sign it is, but either way, it's going to be one of those, and that's good enough for us. Okay, here comes the big chunk of text. Is where we get on to looking at the E4 page. Now, D3 is a derivation. So D3 to the x to the n of x to the n, is equal to n u x to the n minus 1 up to a sign. Right? That's you can show that pretty simply. And so with this information, and oh, by the way, this is because d3 of x is equal to u up to a sign. So now with this information, we can talk about the E4 page. And this is the E infinity page. So more precisely, what we have is that E4 0 to n. So this might be non-trivial. This is the homology of this, okay? And this is going to be this guy here. Now, the image is going to go to 0 because this guy here is equal to 0. And D3, this D3 here, is an injection. And the way that I like to think about why this is because if you think about this, this is pretty much multiplication by n. That's a slightly hand-wavy way to think about it, but if you kind of think about this, replace multiplication with addition and think about the x's and the u's and stuff as being 1s, then you'll get n times, you get 1 times 1 n times or whatever. That's just how I like to think about it. I like to think about this as being multiplication by n, just in disguise. And so because D3 is an injection, the kernel is 0, and so this guy here is going to be 0. Okay. Now we get the non-trivial people on the E infinity page. That is the E3 2 times n minus 1, guys. and the reason I said 2 to the n minus 1 is because it's just easier to see because this is what our D3 is. It looks like. Let's see. So this is going to be the homology because it's the homology of E3. Because homology. Let me just write this out. Homology of E3 2 times n minus 1. That's really bad small handwriting, but hopefully you see what I mean. So it's going to be the kernel with the image at those positions. Now, the kernel of the map is going to be everything, because because the E6, that's out of our zone. That's in our zone, which is 0. So the kernel is going to be everything. So on top, we're going to pretty much get the integers because E3 2n minus 1 is the integers. And then what's it going to be mod? Well, okay, remember how I said that this was kind of like multiplication by n? Well, that does actually work out. That reasoning does actually work out. So we get the integer, we get nz, or z, sorry. And so we're going to get the integers mod n. And so on our page, our E infinity page, is going to look something like this. 0, 1, 2, 3, 4, so forth. 0, 1, 2, 3, 4, so forth. Well, okay, now everything here is going to be 0, 2. Okay, so the only column we care about now is when p is equal to 3. So let's just have this on the side. E4, 3, 2 times n minus 1 is equal to the integers mod n. So our first non-trivial person is when n equals 2. So 2 times 2 minus 1, that's, wait, what's 2? That is 2. So here, okay. So here we're going to get the integers mod 2. Then if we go up by 2, we're going to get the integers mod 3. Then if we go up again, we're going to get the integers mod 4. And in between, we're going to have zeros, basically. And this integer is mod 1, but yeah, no, that's 0. So that's what our E infinite, and everything along here is going to be 0. Everything here is going to be 0. So this is the only page we care about. And so clearly, we're not going to run into any problems, not going to run into any extension problems, if we just sum along the diagonals to get h5 of f. Since remember, our thing is converging to the cohomology of our fiber f. So to get it, we just sum along the diagonals. So 2 plus 3 is 5. So it's going to be along this diagonal here. And summing along it, well, we're going to get a bunch of zeros plus the integers mod 2 plus a bunch of zeros. And so we get that the fifth cohomology of the fiber is equal to the integers mod 2. Now, okay, I'm not going to go over the universal coefficient arguments, but because of this, we can basically drop torsion a degree, and we get our final result like this. Voila. Yeah, that's our result, and, okay, one might think at this point, that was a pretty, complicated computation, just to obtain that this homotopy group of the sphere is the second simplest thing it could be, the integers mod 2. But, that's just the nature of homotopy groups of spheres, I don't think, I think that that's quite an exciting thought, because, well, it's clear that wasn't, impossible, but it was an interesting computation, and, we managed to obtain something non-trivial, and that's always a success, right? So that was a really nice example of computation, and, okay,
just to check quick, this dropping torsion a degree. This is that statement from Hatcher that we looked at sometime about the corollary of universal coefficients or cohomology.
Yeah, okay. I'm pretty sure. I think that I wasn't too thorough to check that everything actually works out, but.
That's fine. Yeah, I trust you. I just wanted to kind of schematically know where that was coming from. Okay.
Yeah, I basically just. Kind of just dropped in the slogan in there, so this didn't seem completely random, and just because I know that this is right, so I just kind of put it,
Yeah, we know the results, so I guess you can kind of work backwards. This implication has to be true. Yeah,
exactly. Okay. Okay, so those are 3 applications or computations, whatever you want to call them. And that took quite a while. I don't know exactly how long that took, but, it took a while. So I'm not going to go over anything else that we can do with the Serre spectral sequence. But, there are many other applications, right? There's this thing called the Wang sequence, which basically what it does is it assumes you have a fibration of this form, and then it gives you a long exact sequence in homology. And similarly, the Giessen sequence does this. and then it gives you a different long exact sequence in homology. So it assumes you have a fibration like this, and then using the Serre spectral sequence, you can derive those things. There's, you have the other computations of cohomology groups which you can do, and there are more homotopy groups of spheres which you can compute with this. So one last thing I'm going to leave you with are 3 exercises which use the Serre spectral sequence. These aren't really in any order of difficulty. Yeah, I'd say these are all pretty much equally difficult exercises. The first one is to use induction to compute the cohomology ring of the unitary group. And the inductive step, well, you have this, and therefore you have the base case being this division algebra. Sorry, I just forgot the name of this.
Exterior algebra?
Yeah, exterior. Yeah, thank you. Yeah, exterior algebra here. And you can use induction to show that the final result is U of n is this exterior algebra, but on x1 up until x2n minus 1. And the inductive step is using the Serre spectral sequence. And of course you assume it for this, and therefore you know the cohomology of this guy by induction, and you know the cohomology of this guy just because he's very simple under cohomology, and then you can try and get this one. The second one is to compute the cohomology ring of the loop space of the n sphere using that path space fibration, whatever. And the third one, something that we were talking about in physics, #physics, I don't know, a couple of days ago, which is the lens space. And using this vibration here, you can actually compute the. Sorry, I don't know why I wrote infinite lens space there. But you can compute the cohomology of lens space too, using this vibration, because again we know this one and we know this one. And I made sure to pick examples which don't run into any extension problems. Just because I didn't cover that in the talk, so blindly following my strategy when there are problems, obviously isn't what I want to encourage. But okay, I think I was talking for what, an hour or something. I don't know if anyone can confirm how long I've been talking for so far.
It's been like an hour and a half. Do you want to take a break and then do the rest of it, or
Yeah.
are people getting tired?
I don't know. Yeah, I'll stop recording here and then